Thank you very much for having me. I'm very happy to present some parts of the KODAQS Toolbox, mainly the TextPrep tool that I prepared for the KODAQS Toolbox, but also some parts of the general conceptualization of the KODAQS Toolbox. So I will start with first introduce myself a bit. So my name is Yannik. I'm a postdoctoral researcher in the KODAQS project, and I was or am responsible for the development of content for the digital behavioral data stream. And I'm currently also part of the Ephemera project at the DSS department at GESIS. But before that, I did my PhD at the University of Bonn in the Research Association NRW Digital Society. And my research interests range from platform studies and governance to digital methods and data quality, ephemerality, and related to my PhD thesis, the European public sphere online. I also want to mention that this tool was not only developed by me, but also by Kunjan Shah, who is currently a student assistant in the KODAQS project, still finishing his master's degree in computer sciences in Paderborn University. And yeah, he helped a lot on this tool. The presentation itself, I would like to first talk a bit about what our understanding of data quality is and how we considered and designed these data quality tools in KODAQS, and then highlight the TextPrep tool and what it does and what it's all about. So this is basically the division of this talk. So data quality, I think, was as a term has a long tradition in social science research, in particular in survey research. But in recent years, it got more and more connected to digital behavioral data as well. For example, in these so-called error frameworks, like the Twitter data quality framework or the total errors framework by Sen et al. So data quality was more and more connected to digital behavioral data as well. But what do we actually mean when talking about data quality in KODAQS and at GESIS? According to Herzog et al., data quality relates to the degree to which a set of inherent characteristics of data fulfills intended operational decision-making and other specific roles. And what we can see with this definition is that there are two components kind of highlighted in this definition. On the one hand side, it refers to a set of inherent characteristics of data, some kind of inherent characteristics of data on the one hand side, but also it is supposed to fulfill certain needs and certain roles. So there's also kind of an external side to data quality. And that's why we came up with these pairs of data quality dimensions, especially Deichler et al. In their recent paper in Social Science Computer Review, between an intrinsic and an extrinsic component of data quality. And the intrinsic component refers to the correctness and completeness of data, which are supposed to lead to the best possible evidence. And then there are like indicators connected to this, like accuracy, completeness, consistency, something like this. But there's also an extrinsic perspective where that is more about the usability basically of the data and whether it fits for purpose. And here we've got, for example, the FAIR criteria, like whether the data is findable, accessible, interoperable, and reusable as typical indicators for the extrinsic side. Beside the intrinsic and the extrinsic dimension, we also have two key terms in KODAQS, which is the measurement and representation dimension. And the measurement dimension refers to that data should allow a valid measurement of the research construct. And the representation dimension is rather about that the data sample should be representative from the target population. And as you can see, when you look in the KODAQS Toolbox, we separated basically our tools according to these two dimensions. So whether we have data quality issues that are more on the representation side or issues that are more on the measurement side. Related to the concrete design of tools in the KODAQS Toolbox, we have some assumption, like some basic assumptions, I would say, and also some kind of requirements of our tools. And I would like to present those in this quickly. The first one is that we consider data quality assessment to be relational and depending on the concrete research question and method. Then data quality assessment depends also on the data type. Data quality assessment can itself be error prone, and data quality tools must be open and actively maintained. I would now go a bit deeper into each of these points and what they mean. So data quality assessment is relational and depends on the research question and methods. To us, data quality is not only or not purely an inherent characteristics of the data, as also mentioned in the Herzog definition, but it's also context dependent. So whether something is of high quality or of low quality must be interpreted against the backdrop of a specific research goal or concrete application context. For example, in quite some studies, for example, when it's about public deliberation in digital public spheres, let's say, social bots in a social media data set might be considered a problem or noise for this specific purpose. If, for example, if it's about studying human communication. But if bots are the main object of study, it's of course not a problem, but very necessary to have these to have social bot communication in a data set. Meaning data quality assessment is relational and depends on the research question and the methods. And tools should require and surface the intended application context and reflect it. Then data quality assessment depends on data type. Here, this means that the data type and the provenance shape appropriate quality criteria. So, for example, while survey data, it's a type of designed data where researchers have a lot of influence on how the data is produced. The social media data, it's of course not the case, as it is rather found data. And we are primarily dependent on social media platforms and how they arrange and structure certain data that we then get access to. Of course, there are also different modalities of data, like whether it's numeric, text, audiovisual, and so on. And data quality checks need to be tailored to these modalities. So tools should record data type origin and offer type-specific tests. Then another important aspect that is also, that I would like to highlight is that data quality assessment, of course, can itself be error-prone, meaning that the quality assessment methods can introduce new errors in the process as well, so which is kind of a quality paradox. For example, there are these bot detection tools, like for example, the botometer. I stick with this bot example for this talk now, that predict how many bots appear in a certain data set. For example, the botometer was linked to the Twitter API, and you could type in certain IDs of users, and they gave back either a likelihood or a value, whether it's like whether this specific user is a bot or not. But some research has shown that they have quite a high false positive rate. And after the changes of the Twitter API due to the takeover by Elon Musk, these tools now rely on outdated training data and are actually not up to date anymore. So they can introduce, if they are used, they can introduce also errors. So the risk basically is that automated indicators can misleadingly signal high data quality when it's not the case. And for this, we must apply the same scrutiny to tools and indicators as to the data itself. And tools must, and for us in the KODAQS Toolbox, this meant that tools should indicate its own limitations and reflect on this. And quality tools must be open and actively maintained. So tools should be findable, accessible, and reusable. So basically the FAIR criteria that is connected to data should also be connected to tools. So requirements are good documentation, versioning, and clear maintenance plans. Many academic tools are developed in time-limited project and lack of long-term upkeep. So that's a challenge. And there's also like these temporal dimensions. Like, for example, as I said, these platform API changes with regard to the bottom meta can make specific tools unusable, and therefore quality assessment can also age. And yes, these are things that we took into account when we produced these KODAQS tools. Yeah, great, which you can see here. And there's also the QR code that you can use to have a look at the KODAQS toolbox. Yeah, with this short introduction in mind, I would now hand or go over to the TextPrep tool. And so the TextPrep tool is a tool that is basically dealing with text preprocessing as one step of the typical workflow when working with online platform data. So what you can see here is the so-called TED-ON framework by Sen et al., which basically maps all potential error sources in a typical research project with online platform data. So going from the construct definition to the platform selection that raises certain error sources on the representation and the measurement level, the data collection, the data preprocessing and data analysis. And it's basically an adaptation of the classical total survey error framework by Groves and Lübeck. And we tried in the KODAQS toolbox, we always tried to connect our tools to certain types of errors that are prevalent in this type of research project framework, let's say. And here it's obviously clear. So TextPrep with regard to text preprocessing is related to errors connected to data preprocessing, and in there it's rather on the measurement side than on the representation side. So within TextPrep, we do not closely look on the user level for certain reasons, but rather on the trace level. So with this, I would like to say a few words about preprocessing of online platform data in general, and in particular text preprocessing. So text preprocessing can be defined as all changes made to the raw text data after the data collection and before the data analysis. The main purpose is to bring the raw data in a form that is then suitable for applying specific research methods. And also, especially with regard to online platform data, we can keep in mind that text preprocessing is actually a major influence that researchers have on the data. I mean, of course, in the normal data collection process of online platform data, researchers have also influence. I mean, they determine the keywords, for example, or the accounts they want to study, but in comparison to survey research, there's way less control in terms, as I said before, like how the platform arrange data, how they structure the data, how they transfer data, how much data researchers get, and so on. But the text preprocessing is a real point of influence that researchers have on online platform data and on the process. And on the one hand side, text preprocessing can reduce the likelihood of errors and arrange the data in a form that it then can be analyzed like in a more appropriate or better way. But on the other hand, of course, it can also introduce errors, like, for example, trace reduction errors, when we remove certain parts from text that might contain important information, for example. And in general, at least for TextPrep, I relate the text preprocessing mostly to the intrinsic perspective and the measurement dimension of data quality. Of course, there's also use case dependency of text preprocessing. So social media data is normally noisier than other types of text data, for example, newspaper articles, research papers, or political speeches. But this cannot be considered necessarily an indicator of bad data quality, as this is just a characteristic of this type of data. Still, this might lead to more text preprocessing being necessary. Another important factor that needs to be considered with regard to the use case dependency is that text preprocessing is highly dependent on the methods of analysis. So for back of word models, for example, if you apply them to in a computational analysis workflow, if you apply them to your social media text data, usually there a high level of preprocessing is necessary for them to work. On the other hand, like with models like based on word embeddings or transformers or LMMs, there is usually low level of preprocessing necessary, or it comes at a later stage. For example, while in topic modeling, for instance, like LDA or STM, which are back of word models, usually preprocess your data like highly before you can to receive interpretable results. With word embedding based topic models, for instance, like bird topic, it kind of switches because there you apply the text preprocessing after the modeling itself. So the function is the same. You want to have interpretable results in the end, but the stages in the process kind of are changing between these types of models. And because the back of word models are highly sensitive to preprocessing and data quality, for this specific tutorial as a use case, we use them as an example. So the TextPrep use case, we created a small artificial social media data set with multilingual posts about the Olympic Summer Games in Paris 24, supposedly collected from the hashtag Olympics 24. That was like our test data set to make it as concrete and as applicable as possible. For ethical and legal reasons, we have not used a real data set, but a synthetic one. As a method, we decided to go for structural topic modeling, so back of words models, as it is highly sensitive to data quality and text preprocessing. And what our aim was to map the impact of text preprocessing levels on the results, which also is not a full, which can be considered a kind of validation technique. I mean, of course, it's not enough. There are different validation techniques for topic modeling, like manual checks, but also these word intrusion tests. For example, Chung Chan has this Olong package for topic modeling validation. However, we consider this to be another type of possible validation. And we used indicators like cousin similarity, semantic coherence, and exclusivity as measures to map the impact of different text preprocessing steps and tools. We based our this tool on the systematization of different preprocessing levels that we took from Churchill and Sign from the article in 2021, who distinguished between elementary pattern-based preprocessing, like removal of punctuation or special characters, dictionary-based preprocessing, like the removal of stop words, natural language processing, like stemming or lemmatization, and statistical preprocessing, like the removal of tokens with high and low frequencies. And what our main purpose in the TextPrep tool was that we wanted to, on the one hand side, compare different strategies of preprocessing within these levels. So, for example, regarding the stop word removal, we wanted to compare different, for example, stop word lists. So within each preprocessing level, but we also wanted to see how these different preprocessing levels between each other impacted the modeling outcome. So I will now briefly sum up a few preprocessing steps that we did to show some functionalities of the tool. So first, because we had this example case with this Olympic 24 data set, this was kind of considered as a transnational media event. And therefore, we also implemented multilingual data in there. And yeah, basically we said that we basically applied 3 strategies of handling multilingual data, which came from the papers from Licht and Lind et al., which are first selecting cases. So basically deciding for a specific language. Second, working with multiple language data sets. So basically dividing the one data set into multiple language data sets, and then do separate analysis for all the different language data sets. And the third one is to use machine translation. We showed all of the three preprocessing steps in TextPrep, but we used in detail, we did some comparisons with the machine translation strategy, as you can also see on the picture on the right. In detail, we compared DeepL API with this Google Translate for our few non-English postings, basically, and use cousin similarity to map how using different translation tools impact the translated data, basically. And here, for example, we had a cousin similarity from 0.88, indicating there is a quite high overlap between the two, but still there are some differences. And yeah, in the end, because yeah, if it would have been way higher, this would have been an indicator for, okay, this specific preprocessing step and this specific decision might have a major impact on the results in the end. This was for these two tools at least not the case. So we needed to decide, with which option to choose. And we found that, and so we made a comparison between the two and found in other studies that DeepL seems to be slightly more accurate than Google Translate. I mean, might have also been use case dependent, but we found these studies. The one advantage from Google Translate is that it contains more languages, but as we had only a few languages in our data set, we went with DeepL in the end. But this is kind of a strategy that we did for DeepL Google Translate here, that we always tried when looking at different possibilities and different strategies to identify how, in terms of similarity between text, how much differences occur when we choose a specific preprocessing step. And by this, our aim was to kind of identify what are the highly relevant decisions to take in the process of text preprocessing to then identify, okay, this is something where we really need to take care and have a closer look because this might impact results. And yeah, a lot of preprocessing actually is kind of normally done by default. So in the typical R packages or in the typical Python packages, there are like default options, and we all tend to use them or use our always the same code, basically. So what we try to do is to really go step by step through each phase and map potential differences and how much of an impact certain decisions have. The second aspect I wanted to mention is the stop word removal. So there are typically also like default stop word list within the normal packages of text processing. For example, in Quantida, I think it was the smart stop word list that is the default. In other packages, it might be different. But these stop word lists were designed at some point, and some words were included, some were not. That might be very different from each other. So we wanted to actually see what happens when we use different stop word lists. And so what you can see there, we compared 3 stop word lists, which are NLTK, Smart, and stop word ISO. On the right-hand side, you can already see that they are quite different in length. So NLTK has 179 stop words, Smart has 571, and stop word ISO has 1,298. So they are in types of length already quite different. And we wanted to see whether how much of an impact this makes. And if you apply them to our sample data, NLTK would remove 914 words, SMART would remove 1065 words, StopRed ISO 1147 words. Of course, this because we only had a very small data set, was I think like 300 artificial postings. This is not in general, it's maybe not a lot, but still for such a small data set, it's already quite a difference. And when we checked manually, we also found that, for example, the StopWord ISO list also removed words that were like relevant to our use case. Also, we found that there are inconsistencies within and between stopword lists. So, for example, in SMART, they include stopwords like, for example, he is, but not she is. So they are in these standard stopword lists. There are also a lot of inconsistencies, and there are also different ways of dealing with contradiction. So, for example, if you have removed punctuation before applying stopword list, this might be, depending on this concrete stopword list, very relevant because some of them might then not work well. So this is also something that we found that needs to be kept in mind. And our solution was in the end that we did a use case specific customized stopword list after manual evaluation. So we kind of made a merge of NLTK and SMART and removed certain words from the stopword list and added certain stopword words from the stopword list. And that was our way to go here. What also has been done, but I won't go into detail into this. So we also, of course, did elementary preprocessing, so removal of special characters, symbols, punctuation, tokenization, and lemmatization. So this was also done, but I would take too much time to highlight every preprocessing step in detail. And then I come to the modeling. So we compared how different, or we wanted to compare how different types of text preprocessing impact key indicators like semantic coherence and exclusivity. And we did so by defining 4 levels of preprocessing and creating 4 document term matrices for this. So we have the level 1, which only consists of 2 preprocessing steps, which is tokenization and automated translation. Then we have the level 1, where we additionally have the elementary pattern-based preprocessing, so the removal of punctuation, symbols, hashtags, and numbers. Our level 2 was additionally with dictionary-based preprocessing, so stopword removal. And the 4th level was also with natural language processing, so lemmatization. And below the table, the first table, you can see like how these DFMs differ, like the number of tokens and so on. Here you can see some of the results when we plotted these models in this graph with the exclusivity and coherence values. So semantic coherence, it is like the more preprocessing steps are applied, the less coherent the model becomes. It's kind of counterintuitive, but it's just that before the stopword removal, the topics include a lot of tokens that occur very frequently in the data, but they make the topics basically not interpretable, which is a typical thing. That's why this step is of course done. However, we can see it. What we can see is that then stopword removal has like the biggest impact because STM2 is like very far away from STM1 in this topic coherence exclusivity graph. So this has the highest value. What is quite interesting is that STM2 has a lower coherence than STM3, and that was the difference between them is that lemmatization come into place. And my explanation for this is that because lemmatization merges words together, this means that the coherence basically increases because there are less alternatives. So that's why I think STM3 is a bit more coherent than STM2 due to the lemmatization. And with the exclusivity, we can see that it increases with greater preprocessing steps because topics just become less dominated by highly frequent tokens. Yeah, so this is basically our outcome when comparing the different preprocessing level and steps between each other. Yeah, so our main takeaways are the importance of evaluating preprocessing steps while suggesting systematic comparison at all levels of the research process to identify an optimal solution tailored to the use case, examined effective approaches within the preprocessing step, but also compared how different levels of preprocessing affect the modeling outcome. And also because we had, when doing preprocessing, there is like nothing as a clear gold standard, so to speak. So what our strategies was to compare alternative options to identify which steps are crucial and have high impact on the results, to be at least aware of what's going on and what's happening in there. And for us, these strategies are essential for making informed decisions during the research project. And when I quickly link everything that I now said to the requirements of our KODAQS tools, so data quality assessment is relational and depends on the research question. So here we had this concrete use case example, even though it was only artificial, this topics of this Olympics 24 data set, which were very connected to how we in the end constructed the stop word list. And also with structured topic modeling, we had a back of word model that came with specific requirements for text preprocessing. Data quality assessment depends on the data type. So here we had the clear focus on text data. So basically text preprocessing is data type specific by definition. But also it was like not only text data, but social media or online platform text data, which is noisier than other data types. And then typical platform specific characteristics need to be done, like, for example, removing hashtags if necessary, for instance. The data quality assessment can itself be error prone. That's why we want to highlight also the limitation of this tool, meaning that, for example, TextPrep is limited to currently back of word models. That would, of course, be a nice addition to also do a similar tool for word embedding based models. Or, yeah. Then we also have to take into account that with the strategy of automated or machine translation within the preprocessing, there is translation variance in commercial models like Google Translate and DeepL because they're constantly updated, they are not open source, and then we might have reproducibility or might receive reproducibility issues. So this is something to keep in mind. Also from a data quality perspective. And of course, also some limitations that we have are just our data set characteristics because it's very small data and it's synthetic data. Final point, quality tools must be open and actively maintained. So TextPrep is fully reproducible. It can be opened on GitHub and BiderHub. It can be downloaded as PDF, Quarto, Jupyter Notebook, and contains JIT versioning for regular updates. As a short outlook, we recently added some new tools to our toolbox. For example, on the topic of automatic machine translation, we added the so-called toppling tool for evaluating the quality of machine translation for multilingual modeling with Nadezhda Otsornia and Mario Heim from the LMU in Munich, the communication departments there. Also with Paul Ballow, Christina Fiemann, Maximilian Linde, Yun Sun, and Chunghan Chan. We did a multiverse analysis of topic modeling to kind of more systematically compare these different decisions and topic modeling. We're also working on a new tool for data changes of social media data sets, so more on the ephemerality side that I mentioned in the beginning. And there, for the final year of KODAQS, there are also new tools on LLMs and AI planned. And yeah, with this, thank you very much for your attention.